Good afternoon. So we left off talking about adsorption isotherms and been talking about adsorption. So that is the attachment of molecules to a surface. We talked about micropores and the macropores within the material, for instance, like an activated carbon material. Now what we need to do is quantify that information and look at how do we use that information in engineering setting. We're not going to go into great detail about this. I do want you to know this information. So as I said, what we're looking at doing is trying to quantify the extent to which a chemical adsorbs, attaches to a solid material. So the way that we typically do this is we run what are referred to as isotherms. Iso, same, therm, temperature. So these are experiments conducted at a constant temperature. Remember, adsorption is exothermic, so temperature plays a significant role. So what we would do is we would start with a set of, you can think of this as beakers. So we start with a set of containers with a the same concentration of a contaminant. So for instance, we could start this with benzene. And each of the beakers or each of the containers would have, let's say, 100 milligrams. Since we're looking at air, we'll say 100 milligrams per cubic meter of air. And then what we do is we're adding the mass of sorbent. So the mass of that solid. And we add different masses in each of the containers. And we have a control that has no sorbent in it. And what we're measuring is the mass adsorbed, so the mass of material that is attached, sorbed to the solid surface, divided by the mass of adsorbent. So kind of think of this the way we have it written. Let's just think of this as representing 3 grams, 5 grams, and 7 grams. Okay. So that mass of adsorbent is the mass of solid. And the mass adsorbed is the initial concentration minus the concentration at equilibrium. Each of these here, this is at equilibrium. If you remember, the sorption process itself is very rapid, but it's limited by what? What limits sorption? The diffusion of that chemical from the bulk phase into the micropores, into the actual sites. So what I've done is I've set up a scenario where we can think of this as we have, let me just draw this as a box. So we have a volume of gas, and you're told that the volume is, and the initial concentration of benzene in the gas phase is 300 micrograms per cubic meter. Okay. And we run this experiment. So we add a certain mass of activated carbon into each one of the 10 vials. First vial is the control, so we don't add any activated carbon. We're using that to assess whether or not we have any losses. And then we measure the concentration at equilibrium. And you see that as we increase the mass of activated carbon, we decrease the equilibrium concentration. So more material is sorbed. Now, what we then do is we take that information and we plot it. And there are a number of what we refer to as isotherm expressions that can be used to describe the adsorption of the chemical onto the solid surface. So there are three most common. There are also many others that are more complicated. The three that are included on the FE or in the FE reference handbook are the linear, the Langmuir, and the Freundlich isotherms. So those are the three that we'll cover. So taking the data that we generated, we can then calculate what is known as X over M, or you'll see it also described as Q sub E. I apologize for the lines today. And we calculate that simply as the difference in the initial and the equilibrium concentrations. So remember, this is milligrams per cubic meter. And we had 2 cubic meters. And then we'll divide this by the mass of carbon. So notice this is in milligrams per gram. So it's milligrams of benzene per gram of carbon. For vial 3, we would have 300 minus 235. Again, we'll multiply that by the 2 cubic meters, so we have milligrams. And in this case, we'll divide by the 10 grams. And that gives us the X over M value. So we have a series of X over M values for the various different conditions. If we plot the 5 values for which there is the greatest mass of adsorbent, you actually see you have a nice linear plot. So we plot X over M versus the equilibrium concentration. And the linear isotherm is typically used for very low concentrations on soils. So typically the ratio of material adsorbent, or sorry, the ratio of adsorbate to adsorbent, okay, is very low. So we have a large amount of adsorbent. If we plot all of the data, you see that it's not linear. And this is a typical shape of a Freundlich isotherm, that it curves like you're seeing here. So it curves like this, and it typically will asymptote out. Now, the Freundlich isotherm is purely empirical. It has no theoretical basis, and it is simply a curve fitting exercise. So we're plotting this as a power function where X over M is equal to some constant K times the equilibrium concentration to the 1 over N power. That is simplicity, that's the Freundlich isotherm. Okay. So just remember this typical shape, and it has no theoretical basis. It's purely empirical. We typically linearize this using a log relationship. So we take in this case, natural log of X over M, that equals 1 over M, N times the natural log of the equilibrium concentration plus ln of K. So 1 over N is our slope, 1 over N is the slope, and the natural log of K is the y-intercept. And we can also plot this as log base 10. So you can either plot it as a natural log or a log base 10. Both cases, you're plotting the natural log or the log base 10 of X over M versus the natural log of the equilibrium concentration. And that gives you the values, as I mentioned, 1 over N times log of K. And you can see that here. So we have a slope. So this is 1 over N, and this is the intercept. So ln of K is equal to negative 1.25. And from that, we can calculate K. Now, we can also use the Langmuir isotherm, and the Langmuir isotherm is has a theoretical basis. And it is equal to, the x over m is equal to A times K, again, times your equilibrium concentration, divided by 1 plus K over the equilibrium concentration. 1 plus K times the equilibrium concentration. This A term is related to monolayer coverage. So we drew the grains of activated carbon. We showed the micropores in it, and we talked about sites on those micropores. So when we talk about monolayer coverage, what we're talking about is one molecule per site. So that we don't have molecules that are associated with one another, that it kind of will stack up on top of one another. So the assumptions in this model are that each active site interacts with only one molecule. So we don't have, for instance, polar-polar or polar-nonpolar interactions between molecules. The interactions are purely between the adsorbate molecule and the site. It also assumes that adsorption occurs on these well-defined localized sites, which we could quantify the number of sites on that adsorbent. Saturation corresponds to complete occupancy. So that's that monolayer coverage. We also assume that every adsorption site is the same as the next adsorption site. So they're all energetically equivalent. We refer to that as homogeneous. And then the other thing that we will assume is that no interactions occur between adjacent adsorbed molecules. So that means that if we have two adjacent sites, we have adsorption at those two sites. The molecules, our adsorbate molecules, don't interact. One molecule is not going to inhibit adsorption of another or speed up the adsorption. And we can linearize this model by plotting 1 over x over m versus 1 over c sub a. So we're plotting 1 over x sub n over 1 over c sub a. Linear plot. The slope is 1 over a times k, and 1 over a is our intercept. So by plotting this, you see here, this corresponds to 1 over a times k, and this corresponds to 1 over a. So once we determine 1 over a, we can determine k. When we're looking at adsorption of gases, we typically operate this in a semi-continuous mode or a column. So we have a column containing the adsorbent, and that we're passing the gas through the column. And what we have is we produce clean gas. So we have our contaminated gas. Coming from that, we have the clean gas. Now, what's shown here is essentially, well, kind of think of it as a time sequence. So we start out, initially we would start out, and we'll do it here. So initially we have a clean bed. So we have carbon that contains no benzene. We'll describe it. We'll keep with the benzene scenario. And what's happening is that over time, you're exhausting all of the sites on a portion of the bed. So here we have C naught entering. From this point here, once we've exhausted all of the sites, the concentration, if we had a port out here and we measured the concentration would be the same as our influent concentration. We're achieving no additional removal. So we're getting removal below, but we're not getting removal in some portion of the top of the bed. And so this was now moved down further. And now the concentration, if we measure here, the concentration is equal to C naught. So we have C naught here, we have C naught here, and we have C naught as it moves down, that gas moves down the column, or the adsorption, what we call the adsorption front, moves down the column. And further, okay, here, again, at this point here, if I measure the concentration, it would be what? So it's C naught. And eventually, we've exhausted that entire bed of carbon, and the concentration leaving is C naught. So we get no further removal in that carbon bed. This region right here is referred to as the adsorption zone. And you can see that adsorption zone moving down the column. And we can quantify the depth of the adsorption zone, or often referred to as a HTU, height of the theoretical unit, exchange unit. And that is related to how effective that carbon is at removing the material. The smaller the depth of adsorption zone, or the smaller the HTU, the more effective the adsorption. So if you're looking at very efficient removal, you want a material that has a small H2U, or sigma, same height of the theoretical unit, or or depth of the adsorption zone. And that depth will vary for each of the contaminants. So for instance, I know a number of you in 495 are designing adsorption columns for removal of PFAS chemicals. It's actually aqueous, but it's the same theory. And one of the challenges, roughly 5,000 PFAS chemicals. There are, most states only regulate 2, PFOA and PFOS. But they behave very differently, and they behave very differently with many of these other compounds. So that makes it difficult in terms of designing a treatment system. Now, the diagram you see below is referred to as a breakthrough curve. So what it's done is they're measuring the concentration in the effluent at any point in time. And breakthrough is defined typically in a regulatory or operational mode. There is no theoretical value for breakthrough. That's just designed, as I said, based on regulations or some acceptable operational limit. The time to breakthrough can be determined by the difference between the height of the bed and the depth of the adsorption zone divided by the velocity, how rapidly that adsorption zone moves down the column. The sharper or the smaller the sigma value, small sigma value, we have a sharp breakthrough. The larger that sigma value, the shallower the breakthrough. And that's important because we want efficient use of the column. So typically we want a small depth of adsorption zone. The height of the adsorption zone is determined a similar way to that used for absorption towers. So when we talk about absorption, you'll see we'll use a lot of the same terminology. We'll use terminology, the HTU, we'll use NTU. NTU is the number of theoretical units, and that measures the difficulty of separation. So the greater the number of NTUs, the more difficult it is to separate and remove that chemical. The velocity of the adsorption zone can be determined using this equation here. So it's using the parameters from the Langmuir isotherm. So the K and the A are from the Langmuir isotherm. And then it's using the gas flow rate, the influent concentration of the gas, cross-sectional area of your column, and then the density of the solid adsorbent and the density of the gas. So we'll work a problem looking at this. We have a situation here where we have a adsorption bed that is 0.5 meters deep and 10 square meters in cross-sectional area. And you're asked to determine the breakthrough time. So how long can you operate this column? You've got a gas flow rate. Notice it's in mass per time. Gas temperature, pressure, density of the gas. You're told the packed bed density of the adsorbent in the column, the influent pollutant concentration, and your Langmuir parameters. Major thing is make sure that K is in the same unit. So for instance, if it's kilograms per kilogram or grams per gram, but it needs to be in the same unit. We will use kilograms per kilogram. And then you're given the depth of the adsorption zone. So I've written out the equations and the various parameters. So the velocity of the adsorption zone is equal to the flow rate of the gas, 1.3 kilograms per second, times 1 plus 124 times the concentration. And we want this again in the same units. It was given in grams, so we want this in kilograms, divided by A, which is 18, times the bulk density of the adsorbent, which is 420 kilograms per meter cubed, times the density of the gas, which is 1.184 kilograms per cubic meter, times the cross-sectional area, which is 10 meters squared. And that is equal to 1.8 times 10 to the minus 5 meters per second. So that's the depth, sorry, the velocity by which that adsorption zone is moving down the column. The time to breakthrough is equal to the depth minus the adsorption zone depth, and that was 0.03. Again, make sure that those are in the same units, so both meters, divided by this velocity, and that is equal to roughly 26,000 seconds, or 7.25 hours. So it takes roughly 7.25 hours for breakthrough to be achieved. Now, if we kind of think about how we can change parameters, that would mean every 7 hours, we would either have to replace the activated carbon or desorb that benzene from the column, concentrate it, and capture it. Let's see what happens if we double the depth of the bed. So instead, we have 1.0 meters. So that changes our time to breakthrough. That's equal to 1.0 minus 0.03, and that's 15 hours. So we can almost double the time to breakthrough. So now it's only roughly it's less than twice a day that we would need to shut down that column and regenerate. We could also double the cross-sectional area and make that 20 meters squared. So if that's the case, then the velocity of the adsorption front becomes 9.1 times 10 to the minus 6 meters per second, which means for a depth of 0.5 meters, we would have a breakthrough time of roughly 14.4 hours. And if we went to a 1 meter depth, then our time to breakthrough would be 29.7 hours. So we can modify these parameters to try and increase the time to breakthrough so that we're not having to stop the system and regenerate as often as that original design. Any questions? From here, you should understand the importance of removing VOCs. We've talked about pollution prevention. We talked about condensation, adsorption. We've done a design for an adsorption device. Next week, we'll talk about absorption and incineration.